41. Let's go. A horizontal plane supports a plank with a bar of mass something placed on it. So you got a plank. Supports so a plane supports a plank. Okay. Attached by a light elastic non-deformed cord of length L naught is equal to 40 centimeter to a point O. Wait, what? Another plan supports a plank. So this is just a plank. Okay, not saying anything on it. So with a bar of mass, okay, some mass attached to it and attached by a light elastic non-deformed cord of length something to a point O. So figure one. Okay, you gave us the figure, right? 1.35. It's not 1.35. It is 1.35. Oh, this. Okay. So right, got a plank. You got a mass and some rock. Okay, this string. Fine. Non-deformed cord of length. Fine. The coefficient of friction between the bar and the plank equals. Okay. The plank is slowly shifted to the right until the bar starts sliding over it. All right. It occurs at the moment when the cord deviates from the vertical by an angle of 30 degree. Fine, fine, fine. Find the work that has been performed by the moment of friction force acting on the bar in the reference frame fixed to the plane. What? By that moment, okay. Find this friction force, and then in the reference frame fixed to the plane. That is very different. So you got a pseudo force acting over here. Okay. You also have this tension pulling it. Oh, this is going to be really hard. So cord deviates by some angle, right? Wait, if the cord deviates, then uh-oh, but then the height will decrease if it starts to deviate, right? So it's a light. Oh, yeah. So this cord actually is elastic, right? Mm-hmm. Okay, coefficient is given, coefficient of friction. The spring constant of this cord is not given. That is not correct. But it's elastic. So okay, it will deviate like that. Fine. But then how can I figure out anything? Because if we don't know what this force is, this is going to be not doable. 0 point the bar and the plank equals. So yeah, what quantities do we know? We know the mass, okay, of this bar. We know the length of the cord. Okay, cool. The coefficient friction, okay, we know that. So basically, like they give us what mu should be. Okay. The plank is slowly shifted to the right until the bar starts sliding over it. It occurs at the moment when. Oh, so when this said, when they gave us the angle when this happens to theta naught, right? Whenever it will start sliding, they actually are giving us the spring constant using that. And we just want to find the work that has been performed by that moment by the friction force acting on the bar in the in the reference frame fixed to the plane. So fixed to the plane, this mass does not gain any velocity, and that just means there's only this string force doing work, and at the same time we also have friction doing work. And then there's also the pseudo force that is also doing work. Actually, no, that is not doing any work because this did not move in the first place. So yeah, its displacement is 0. That means that is actually doing any work. There is friction force, which also should not be doing work because yeah, huh. If it's not displacing at all, then how come friction can do any work? But you want acting on the bar in the reference frame fixed to the plane. That is why. Uh, yes, work energy theorem works in that case, but then this is weird because the friction is, I mean, the bar is not like displacing as seen by this Planck's frame. So the F dot ds for the friction is just 0. and that will mean that there is no work done by the friction. But oh well, but there is definitely work done by the string force. No, there is no work done by the string force as well. So work energy theorem works perfectly in the reference frame of the Planck as well, because I mean change in kinetic energy is zero. Also, it's stationary, so there's no work done by any force on it. So you can just shamelessly say zero, right? If it was in the ground frame, it would be different. But since it's just like that, you can just go and say zero, right? Right. So it's just sticking to the plank until 30 degree, and then it will start sliding down. That find the work that has been performed by that moment so till that moment, by the friction force acting on the bar. Exactly, it's gonna be zero. So there we go. 141 0. 142. A smooth light horizontal rod AB can rotate. Where did it go? Right, can rotate about a vertical axis passing through its end A. Smooth light horizontal rod AB. So you got this rod AB rotating about vertical axis passing through end A. The rod is fitted with a small sleeve of mass M attached to the end A. Okay. Wait, it attached to the end A. By a weightless spring of length. Okay. It's different. Fine. So you got something like this, huh? You got this A, you got B. This thing is a spring right here. You got this sleeve attached to it. Yeah. So length L naught and stiffness X. They said X. I'm gonna use K. Whatever. What work must be performed to slowly get this system going and reaching the angular velocity omega? So the rod is light, right? Exactly. So yeah, what work must be performed so that it reaches omega? So it's just the change in kinetic energy plus the change in the potential energy, right? There is change in potential energy because this spring will start to go to whatever length it will go, right? So first of all, when will this be in equilibrium? So in the reference frame of this rod AB, there's the centrifugal force pushing it away, and then there's just the spring force pushing it towards the center. That just means kx. So whatever x naught value you will have, that will be, so here k is the stiffness constant, is equal to omega squared r, actually m omega squared. So m omega naught squared, and then you got r will just be, in fact, uh, yeah, well, initially it was just L naught, right? So it's gonna be L naught plus X naught. From here, you can figure out what X naught should be. So that's one equation. And then what we are interested in is just to figure out the change in kinetic energy, which is half M, so half I, which is going to be M R squared, which is like L naught plus X naught. Yeah, that thing squared, that's omega naught squared. Okay. And that plus the change in the potential energy, which is just half k x naught squared. Yes. Cool. Now, yeah, well, one thing we can say for sure is like just multiply this by L naught plus X naught on both sides, and you will get one thing for sure. So you just get k x naught L naught plus k x naught squared is equal to m omega naught squared times L naught plus X naught squared, right? Now once you have that, you can just put whatever this thing is as this thing, and then you'll just have this whole thing being just kx naught squared. Now, so the main goal is to just figure out what your x naught really is, or what your kx naught is. Once you figure out that, you will find the energy, and that's what we want to find, right? Yes. That's how it should be. Okay, let's find out x naught. So it's gonna be k minus of m omega naught squared times of x naught is equal to m omega naught squared times L naught. So there we go. It's gonna be k times of this quantities first, like it's got m omega naught. So I just use omega squared because they are also using omega squared. So yeah, upon k minus m omega squared and all of that to the power of 2. Yes, that should do it. Okay, this was easy. So 142 done. Let's go to 143. A pulley fixed to the ceiling carries a thread with bodies of masses m1 and m2 attached to its end. Okay, pulley fixed to the ceiling carries a thread with bodies of masses m1 and m2 attached. Okay, to its ends. Wow, easy. The masses of the pulley and the thread are negligible. Friction is absent. Find the acceleration of the center of inertia of the system. Are you serious? Okay, this is actually going to be, yeah, I mean, think about it. It's just m1, m2. You just have to find the actual acceleration of each m1 and m2, and once you do that, right, it will be doable. Exactly. So let's just say that I'm gonna draw this unequal so that it will be a general case. This thing is just m1. This thing is, well, I mean, in the end acceleration, I mean, if this is going, let's say, up by, first of all, just figure out what the acceleration should be, and then we'll carry on with the task. So this will be like tension, and then summation of ni squared upon, yeah, well, that was the thing, right? The coefficients. So it was like t dot x, and then each of these just, so each of these x values, I mean, you differentiate it twice, of course. So t dot a, I should say. So the accelerations were just, why can't I remember what method that was? So it was like something like tension, each e out, and then just each of these just had coefficient over here. So ni, and that times of, so it's just going towards the string, and that just means ni times whatever the base t value is, and that upon the mass, and that minus g. This should be equal to 0. That's what the thing was, right? So just have t summation of ni squared upon mi is equal to, it should be g effective, right? Is equal to summation of mi, oh, sorry, it should be ni, nigi, sorry, nig effective of each of these. So just put I over here. Probably that makes sense. Okay, cool. For this particular case, what you have is like tension, and then you got 1 and 1, right? So you got T pulling up, T pulling up. So it's just going to be tension into 1 upon M1, and then 1 upon M2 is equal to, yeah, each of these just has G as the G effective. So this will just be 2G. There we go. So our tension we can figure out. We just want the acceleration anyway. So it's going to be T upon M1 times, we're doing m1 plus m2 upon m1, right? Which will just say it's 1 plus mu. Yeah, and now I'm gonna use, and I'm gonna pronounce this mu and not eta and whatever, but you get the idea. It's just some symbol. So you can figure out what t upon m1 should be through this thing. So it's just gonna be 2g upon 1 plus mu, where mu is just m2 upon m. It should be not, it should be like this. Okay. Let's not use that. Then we'll just use, first of all, let's write it normally. It will just be m1 plus m2 upon m2, right? So this will be like m2 upon m1 plus m2. So yeah, what we'll do is just define m2 upon m1 to be mu, and then it will just be 2g mu upon 1 plus mu. Once you do that substitution, what we really want to figure out is g minus t upon m1. And did they say anything about this being bigger or something? I don't know. Weird. So this is the acceleration of this guy downward, right? So this will just be equal to, and in fact, since we are just looking for that, why not just, you know, yeah, once we have the tensions, why not just do this thing directly? That just figure out the total force on this system. So this is the system, right? You got the 2t upwards, you got 2, so not 2, m1g and m2g downwards. So the acceleration will just be m1 plus m2 times g downward minus 2t, and that all of thing, all of that upon m1 plus m2, right? That is really what we want to figure out. So you can just get rid of all of this and just figure out what this should be. Okay, cool. So this is just going to be g minus 2t upon m1 plus m2, but you know that t is just 2g m1 m2 upon m1 plus m2, right? So yeah, this upon m1 plus m2, and then 2 times of that is going to be 4g m1 m2 upon m1 plus m2 squared. That's the acceleration. It's this thing downward. Okay, cool. Okay, 143. What did we have to find the acceleration of the center of inertia of the system? Fine, it's going to be this much downwards. So, or let's just go with, I don't know, g times of 4m1 m2 upon m1 plus m2 squared minus 1, this much upwards, right? So this times j hat. Okay, cool. Let's go to 144. Two interacting particles form a closed system. So figure 1.36, where is it? Okay. Two interacting particles form a closed system whose center of inertia is at rest. Figure 1.36 illustrates the position of both particles at a certain moment and the trajectory of the particles, a particle of mass m1. Okay, cool, something like that. And they are saying the inertia, okay, the center of mass is at rest, huh? So the weighted average of these, okay, that is at a constant point, huh? Oh, you're gonna find the trajectory of the particle m2. If it's at rest, then its velocity will always be, oh yeah, I mean, you can do that, sure. Okay, if m1 m2 is equal to m1 upon 2. Okay, cool. So let's just go with that fact that let's just say m2 upon m1 is mu, and then you want to figure out the trajectory. Well, so the center of mass, wow, it's gonna be complicated because, so should we deal with velocities or should we just deal with, I don't know, well, I mean, okay, think about it. So the center of mass will just be m2 x2, when x2 is the position of the second guy, and then plus m1 x1 upon m2 plus m1, which is basically just this mu times x2 plus x1 and that upon this plus 1, right? That is equal to the center of mass. Now let's think about it. This trajectory that drew, now some trajectory like that, and then you gave us the initial positions of these two masses. We know that in the end all you're doing is just putting this into some kind of ratio. So whatever, the center of mass will be like here, and then this will be like, this whole length will be mu more than this length, right? Because m2 was, yeah, that's why. I mean, it's more inclined towards m2. Okay. Does that even make sense? It's got to make sense, right? I mean, that's how the center of mass works. And then we need to figure out trajectory of this thing. How do we do it? So as this guy moves, this thing, okay, this is like, it moves about the center of mass, so it moves about a certain point, and for each of these points you have a certain point like this. Okay, but just drawing it with free hands, that is not easy to do, you know, right? That's definitely not easy to do. Drawing it with free hands is kind of, I mean, since it involves all of this drawing and stuff, it's better to just not do it actually. I know this path will be like of I mean, this is a constant, I mean, yeah, I mean, this ratio is constant, so you're going from here to here, the same vector but multiplied by something, that will be this thing. So given what this position is. You can always figure out what this position is. Yes, but if this was given in equations, it would have been, I mean, doable. But like just like that, no, I cannot. I cannot draw it. Okay, I can never draw an accurate graph of this. Let's go to 145 then. Okay, a closed chain A of mass m is equal to 0.36 kgs attached to a vertical rotating shaft by the means of a thread. Figure 1.37. Why is this so? Okay, just zoom out a bit. 1.45, right? Zoom out even more. So a closed chain A of mass m is equal to whatever is attached to a vertical rotating shaft by the means of a thread. And rotates with a constant angular velocity omega. Okay. The thread forms an angle theta equal to 45 degrees with the vertical. Fine. Find the distance between the chain center of gravity and the rotation axis and the tension of the thread. So this is not ever okay. Maybe it's doable. So find the distance between chain's center of gravity and the rotation axis. So that's how this tension doing this thing. Okay, understand that. And then if this is in steady state, then it's not going down. So if this is a chain of mass m, right, this whole system's center of mass is not, I mean, it's not, its y coordinate is not decreasing or anything. So this guy, okay, there we go. It's got theta angle made with a vertical by this string. You got tension over here. So t cosine theta must be mg. And that just means the vertical, sorry, the horizontal one will just be, yeah, it will just be mg. Wait, what else? Mg tan theta, right? So you know what forces are acting on this thing, and now what? Now that we do these forces, if there's mg tan theta, if it is required, then that just means that this center of mass's acceleration is mg tan theta inside, basically. Sorry, g tan theta towards the center, right? That should do it. Yeah, I guess so. So you can just figure out, I mean, yeah, so g tan theta is just going to be omega squared r. So r can be figured out from that, and that's just the distance of center of mass from this vertical axis. No problem, right? Yeah. Yes, that should work out. So what did I do at this moment? Like, how did I come to this conclusion? What I did was, you have this body, whatever kind of 3D body it is, it's rotating with omega, and in the vertical direction, it's not moving or anything. Nothing's happening. It's just rotating. All right. So I just took the reference frame of this rotating body. Then there's the centrifugal force acting on each of these particles, right? So in the end, you just have the centrifugal force basically acting on the center of mass. Yeah, yeah, you could do that actually. I guess that makes sense. Okay, it's also rotating, and it's the first case of my derivation at yeah, of my derivation that I did back then. So basically, it's that special case where the rotating body, I mean, and the rotating frame both are the same thing, in fact. Okay, so you just got the centrifugal acceleration acting everywhere. Yes, it's just going to be omega squared r, and it's pointing like that. And I mean, I know it's just omega squared r vector, in fact. So I should say omega squared and r vector. So for each of these, actually I should say mi omega squared r vector. So what do I mean by that? So you can just think of this body as a bunch of particles of mass mi. I mean, each having mass mi and position vector ri from some certain origin, and then the yeah, well, well, let's just say Ri is the xy component and not the total position vector, right? So I mean the z component manages itself anyway. Just think about the xy component. So it's just yeah, and then just sum this up and then divide by the summation of mi basically. Yeah, like summing this up, this is just going to be omega squared summation of mi ri, right? This is just m basically. This quantity, what is this actually? Like this is just the centrifugal force felt by each particle, so added up, which is basically the total force experienced by this body. Yes, I mean there's only centrifugal force, nothing else is there. So just a total force experienced by this body, that upon m, and that's equal to, of course, is omega squared and the summation, all that stuff, right? Exactly. So this thing upon mass, so it's just going to be omega squared times the xy radius vector of the center of mass. And yeah, I mean it's pretty elementary. So it's very clear that omega squared r will be equal to j tan theta, because the centrifugal force must be countered by this force, so that this actually is an equilibrium throughout in this particular reference frame. Fine, and that's it. So once you have this, just put this value in there as the answer. Oh, and you also want to find what? The tension, right? So the tension is just I mean, okay, just draw that once again. You got theta right there, this is mg. So mg upon cosine theta is just the tension. So tension is just mg upon cosine theta, mg sec theta, if you will. And the distance, which they didn't give a symbol for, I guess. So 45th. Nope, they didn't give a symbol. I'm just gonna call this thing like RCOM, whatever. That will just be g upon omega squared tan theta, right? That should do it. Now maybe you should calculate it first for these values. Okay, cool. So let's do it. Now I'm gonna zoom in. Okay, so they gave us the values as theta is equal to 45 degrees, so tan theta will just be 1, and then g is, we don't know, just assume g to be 10. Omega squared, 35 squared basically. So this whole thing will just be 10 upon 35 square, right? And I guess this is, so unit wise, g will be like meter per second square, omega is just per second, omega square is just per second square, so meters makes sense, right? So this will just be 10 upon 35 square meters, yeah, which I don't want to do. Oh, we could just do 9.8 upon 35 square, right? So it's gonna be 9.8 is like 1/5 of 49, and that upon, so 35 square will just be 5 squared, and then you got 7 squared. That's why this cancels, just get 1 upon 125, which is like 8 upon 1,000. So 0. Yeah, you get that. It's like it's just 8 into 10 power negative 3. Cool. Meters. And this quantity, so the tension is just, well, what's m? M is 0.36, but 0. Kgs. Oh, it's gonna be 360. Oh, yeah, I mean kgs is as average. Sorry. Gravitation is just 10, and then you got secant theta. So theta was 45 degrees, sec theta will just be square root 2. So just got 3.6 square root 2 as the answer, which I won't deal into. So I'll just leave it like that. Okay, 140. What was this? 146. Okay, a round table. What? No, a round cone A of mass m is equal to 3.2 kg and half angle alpha is equal to 10 degree. So they give a figure as well. Okay, this round cone rolls uniformly and without slipping along a round conical surface B, so that its apex O remains stationary. Figure, okay, whatever. Yes, the center of gravity of the cone A is at the same level as point O. Okay, so it's just understandable. So it's just non-slipping, and it's just rotating one. Okay, I understand that. So you can just figure out what the half angle of this lower cone is. Fine. Through this statement, yes, center of gravity is the same as O, and distance L is equal to 17 centimeter from it. The cone's axis moves with angular velocity omega. So this axis, huh, it moves with omega. I mean, you could just take the rotating frame of this moving cone, I think. The static friction force acting on the cone, if omega is equal to 1 radian per second, and at what values of omega the cone will roll without sliding if the coefficient of friction between the surfaces is equal to k is equal to 0.25. So first part is the static friction force acting on the cone. So there's friction, understandable, and yeah, well, it's just rotating. Huh? Oh, it's kind of complicated. So, oh, this is how do I do it? How do I do this? It will be like normal to the normal, okay, tangential to the surface, right? And yeah, all in all, it's just going like, okay, I understand this. I see how the friction is behaving. Yes, the normal will change everywhere. That's the problematic thing. Oh God, normal is going to change everywhere. I will have to take the reference frame of this rotating cone, in fact. Oh, this isn't good. So you will have some pseudo forces acting everywhere. Uh, that won't do it. I just won't do it. I wish there was some other way to do it. What about the total torque equation? So in vector form, that is. I guess you could do that. You got gravity acting on this cone. So uh, let's just deal with the torque about the point O. Yeah, that should do it. The inertia of, okay, this is bad. I don't know what the inertia of this cone is. In 1.38. Okay, sorry. What question was this? 146, right? The inertia. We don't know what the inertia is. And is this hollow cone or what? From the figure, it looks like it's not hollow because it has these. Okay. So if it's not hollow, you have to find the inertia and then you will have to figure out the actual torque, that's the vector. First of all, let's see if we can actually figure out the torque. So you got friction, yes. The friction also varies. Oh, not good. Not good at all. If it's, it rotates with what? So half angle is one, rotates uniformly without slipping. Fine, so its angular momentum change, we can actually deal with that. But the actual torque, how do you figure that out? We got the gravity acting on it, yes, but that is just completely destroyed by the normal force. So no problem. Yeah. So there's no torque in. Actually, there must be, right? There must be torque in. Come on, think about it. This cone. So to the top view of this cone, we'll just talk about that. This guy is the center of mass is rotating along this, and then you just have the torque going up because of that. But at the same time, you also have this angular momentum vector, so about the center of mass, right, which is also rotating, and then this thing is moving. So yeah, like that and like that. So that means that torque will be going in this direction. So there's two components. One torque is vertical and one torque is like this. So where does this torque come from? The friction provides a torque that is okay. So the friction is providing the other torque, I guess. Think. There's normal force, there's gravity, there is the friction force. What other force would be there? I mean, okay, think about it. Think about just the center of mass. The center of, I mean, since it's rolling with constant angular velocity, there should be no tangential forces. Yes, that's granted. So the friction force should, I mean, okay, sum up to zero in that case, huh? But how can that be? Uh, and still produce a torque. Okay. This is very weird. Friction force will produce a torque as well as be summed up to zero. Okay, at this point I think we should stop. So, like, this is one of those questions that needs more time, right? Because I have no idea how I would do this. I could think about going to the rotating frame of the XOA, yes, and then there will be pseudo forces acting on it. So there's a centrifugal force on each of these particles on this cone, right? There is the, since it's just rotating, wait, oh yeah, like each of these particles is rotating with a different angular velocity. In fact, ooh, that is really bad. So that force will also be there, which will be like pointed radially and everything. And it's going to be very, very hard to do it. Yeah, because okay, the origin is not moving. Good thing. That's not really helpful because it's not planar motion in the first place. It is 3D and fine. So I will need to do it first myself and then I'll see you guys the next video. Okay, bye.